In this video, I'm going to go over how to find various distances in R2 and R3 between points, lines, and planes. So there's a number of different cases here, whether you're in 2 dimensions or 3 dimensions, whether you have point, lines, or planes. And what I'm going to try and do is, because for many of these, there's several different approaches you can take, so there's different ways that you can arrive at the distance. But for each of the different cases, I'm going to try and go over what I think is the most efficient or the easiest way to understand conceptually and computationally, and then go through a quick example of it, rather than go through like a detailed list of all the different approaches that could be taken. So I'm going to start off with the simplest cases with lines. So we're going to start off just the distance from a point to a line in 2 dimensions. So we're going to start off with the case that we have a point up here, not on a line, so let's call that point P, and let's say it has coordinates x1, y1, and then we know some other point on the line Q over here, let's call that x0, y0, and let's also say that we know a normal, so we have a perpendicular to this line. So we'll call this vector n. Now the idea is that we're going to look at the vector from Q to P, and the distance from the line to the point should be the normal component of that vector. So if we go ahead and draw this vector here, so here's the vector QP, and if we think about breaking down this vector into 2 components, one that's in the direction of the line, the other one that's normal to it, then what we get is these 2 pieces. And this red piece here, that's the one that we want to find the length of that. So this is the projection of the vector QP onto this normal n. Alright, so we want the length of that. Now, the signed length of that is the component, but we don't care about the sign. We don't care whether it's positive or negative. So that means the distance between the line and the point is going to be given by the absolute value of the component of QP along n. And if we remember the formula for the component, this is just going to be the absolute value of QP dotted with the normal divided by the length of this normal. Now there's a special case of this that comes up a lot, and that's if you're actually given the equation of this line. So let's say that we actually know that this line has equation ax plus by plus c equals 0. So we have what we've been calling the general form of that line. Then what we can do is we can get a very nice form for this formula. Because in this case, we know that the normal is given by just the vector AB. Okay, we talked about this when we went over normal forms of lines, normal form of a plane. So if the line is given by ax plus by plus c is equal to 0, then a normal is given by AB. And we can take QP, we can just figure this directly. So QP is given by the vector, since it's a vector from Q to P, it's going to be x1 minus x0, y1 minus y0. And now we can substitute in and see what we get. So we get that the distance is, so if we dot QP with n, we're going to get the absolute value of A times x1 minus x0 plus B, y1 minus y0. And this is all going to be over the norm of n, which is going to be square root of a squared plus b squared. Now what I'm going to do is just do a little bit of algebra on here, and you'll see that this is going to work out to something even better. So if I distribute the a here, we can really write this as ax1 minus ax0, and we can write this as by1 minus by0. But we have ax1 plus by1, so if I were to add and subtract a c from there, since I know the point Q, x0, y0, is on the line, I know that a x naught plus b y naught plus c has to equal to 0. So I've got a minus ax naught minus by naught. If I could just get a minus c in there, then I could get all those terms to go away. So that's what I'm going to do. I'm going to add c and subtract c inside here. So plus c minus c. Sorry, let me put it this way. Plus c minus c. There we go. Okay, so what I'm going to do is collect these together. So this one, and this one. We know that all three of those go to 0 because they're all minus ax naught minus by naught minus c. So those all go away. And what we're left with is ax1 plus by1 plus c, which is really just plugging in this outside point that's not on the line and just plugging it into the left-hand side of the equation of the line. And that's what makes this a nice form that's easy to remember. So our formula then just becomes absolute value of ax1 plus by1 plus c, all divided by square root a squared plus b squared. Okay, so let's look at a couple quick examples. We're going to find the distance from the point 2, 7 to the line x plus 3y equals 6. So since we're given the equation of this line, we can use the formula that we just got. So this distance is absolute value ax1 plus by1 plus c, all divided by square root a squared plus b squared. Now, one thing you have to be super careful of, if you're often given a line in this form, you have to remember that this is x plus 3y minus 6 equals 0. So you have to subtract the constant to get it to the other side. It's probably the most important thing that people mess up on this kind of problem. So if we plug in the points, now we're plugging in 2, 7 is the point we're plugging in. So we've got 1 times x plus 3 times y minus 6, that's the plus c, all over square root of 1 squared plus 3 squared. Okay, and that's going to make 21 and 2 is going to be 23 minus 6, so we get 17 on top over square root 10. And that is the distance from the point to the line. Okay, let's look at another example, but this time we're not going to be given the equation of the line, we're going to be given parametric equation of the line. So we're going to find the distance from the point negative 1, 5 to the line with these parametric equations, 1 plus 2t and minus 1 plus 3t. So let's go ahead and sketch the point and the line, and that's the distance that we're looking for, that line segment there. So in this case, we have to come up with a point. Now we can use just the point that's given from the parametric equations. So we can use the point q, which is 1, negative 1. And p here has negative 1, 5. So qp is the vector negative 1, subtract 1, 5, subtract negative 1. So that's negative 2, 6. Now, how are we going to figure out a normal here? So what we have to do here is think about this particular, from point Q up to this other point that I drew here, and think of that as a direction vector for the line. So if we read off the coefficients of t, a direction vector for the line is going to be given by 2, 3. And if you think to your knowledge of perpendicular lines from algebra, you know that the slope that's perpendicular to a given slope is the negative reciprocal. And what that amounts to in component form is that the normal is given by switching the components and then changing the sign of one of them. So instead of 2, 3, it's going to be negative 3, 2. So see that the slope for this direction vector would be 3 over 2, 3 halves, and this one is negative 2/3. QP, we've got n. Now we can plug in and find the distance. So it's the absolute value of QP dotted with n, all divided by the norm of n. So QP dotted with n, see, negative 2 times negative 3 is going to be 6, plus 12, 6 times 2, all over absolute value of n, that's going to be square root, or so the norm of n is going to be square root 9 plus 4. So we get 18 over square root 13. That distance is about equal to 5. It's just less than 5 units. So that's how you find the distance from a point to a line in 2 dimensions. Now we're going to look up to 3 dimensions. What's the distance from a point to a line in 3 dimensions? And this is going to be a little bit different because of the added dimension. It makes it a little bit trickier. So there are actually several different ways that you can go about figuring out this distance. I'm just going to present the way that kind of takes advantage of some of the operations we've talked about here with vectors, and I think this is probably the simplest computationally. So our setup is going to be this line with a point Q on it and direction vector D, and another point P not on the line, and what we want to do is find this distance here. Okay, so the easiest way to do this is to think of the vector from Q to P. And then we're going to think about the area of the parallelogram spanned by that vector QP and this direction vector D. Okay, so let's draw that parallelogram. Now, we know geometrically from the properties of the cross product that we studied that the area of this parallelogram is just equal to the length of the cross product. So it's just the norm of QP crossed with this direction vector D. However, we also know that the area of the parallelogram also has to equal base times height. That's just the area of a parallelogram. Now, what's the base? Well, the base is just the length of the direction vector D. And then the height is the distance that we want. So D. D is always the distance here. So this has length D. So setting these two equal, that just means if this has to be equal to this, it just means that the distance is going to be the length of the cross product divided by the length of D. And that's really the easiest way to find this distance from a point to a line. So the only real thing to say here that might be a little bit tricky is, if you're given symmetric equations, then you have to actually figure out the direction vector. That's not much to do. And you have to find, or you have to observe one particular point, just pick a particular point, Q, on the line. Okay, but these are not really difficult things to do. So once you get the point Q and you get the direction vector D, then you go ahead and use this formula. Right, so again, let's look at an example. We're going to find the distance from the points 3, negative 1, 4 to the line with these given parametric equations. Okay, so the first thing is to figure out a point on the line and our direction vector. And that's not very difficult from the parametric equations. We could take a point, Q, just to be 4, 3, negative 5. That's just taking t equal to 0. 4, 3, negative 5. And since p is equal to 3, negative 1, 4, we get that QP is equal to 3 minus 4, negative 1 subtract 3, 4 subtract negative 5. So negative 1, negative 4, positive 9. Our direction vector comes then from reading off the coefficients of t. So we got negative 1, 2, 3, and that's going to be our direction vector. And now we're equipped just to plug into the formula. So the distance is the norm of QP cross D over norm of D. I do need to figure out what this cross product is here, so let me just do that on the side real quick. When I go to plug this into the distance formula, there's a thing you can do that I can take out a 6. So I don't want to actually say 30 squared plus 6 squared plus 6 squared, so I'll show you that here. So what we do is we get the norm of this negative 30, negative 6, negative 6, all divided by the norm of negative 1, 2, 3. But if you remember the properties about the norm of a vector, I can take out a constant as long as I take out the absolute value of it. So I can pull out a 6 from here. There's a constant of 6. Actually, it's -6. But when I take it out, it's in absolute value. So it's really 6. So I get 6 times the norm of 511 divided by the norm of -123. Okay, and now we can go ahead and do this. This is square root 25 plus 1 plus 1 over square root 1 plus 4 plus 9. And so we end up getting 6 times square root 27 all divided by square root 14. And okay, 6 square root 27, so that can be written as 3 square root 3. So I could write this as 18 square root 3 over square root 14. I could also rationalize this. You could just leave it like this, that would be fine. But if I do rationalize it, then it's going to end up being 9 square root of 42 all over 7. And that's really close to 8 1/3. To 2 digits, it's actually 8.33. Okay, now we're going to turn to parallel lines. So how we find the distance between parallel lines in 2 dimensions or 3 dimensions. So if we think about what's going on here, so we're either in R2 or R3. So in each case, it basically boils down to the previous case, in the sense that all we need to do, well, first of all, I should say, you need to really make sure that these are parallel lines. So before you go ahead and do this, definitely make sure that they're parallel lines. But then what you need to do is just pick one point on one of the lines, any point, and then just use what we did previously about finding the distance between a point and a line. So just find some point, say here P, or here P, and then just do what we did previously. So in the R2 case, you'd be thinking about the components of the normal, so you'd have to figure out a normal vector to the other. Well, it'd be a common normal vector to both of them. And in R3, then you'd also be looking at a direction vector, so the common direction vector for the 2 lines. So let's look at a couple examples. Find the distance between 4x minus 3y equals -1 and 4x minus 3y equals 7. So clearly we can see these lines are parallel. They're written in the general form where we can read off the normal for -3 in each case. So there's our 2 lines. Okay, so let's pick a particular point. Let's pick the point 1 minus 1. That's a real nice one to figure here because we can just say 4 plus 3 is 7. So 1 minus 1 is a point on 4x minus 3y equals 7. So this is 4x minus 3y equals 7. And the one that's above has the equation 4x minus 3y equals -1. So we've got a point. And what is a normal vector? Well, again, since we know that a normal vector, we can just read off from the components here. We know that a normal vector is going to be given by 4, -3. So we just need to find some other point on the other line, Q. So let's take this point here, Q. We can take that to be -1, -1, which means our vector QP is going to be equal to 1 subtract -1, -1 subtract -1, which is going to be 2, 0. And you can see that over here. If you just draw this vector from Q to P, you can see it's going 2 units to the right, and then no units up and down. All right, so we've got all the ingredients now. We just plug in, we've got the absolute value of QP dotted with n, all divided by norm of n. Okay, so 2, 0 dotted with 4, -3, that's going to be 8 plus 0, 16 plus 9. It's a Pythagorean triple, so we get 8 over 5, which is exactly, of course, 1.6. Okay, what about parallel lines in R3? So first of all, let's check to make sure that they really are parallel. So let's look at the direction vectors. Let's say this is L1, and let's say this is L2. Then the direction vector of the first line is 4, 2, 4. Right, it's from there, there, there. The direction vector for the second one is 2, 1, 2. So we see that D1 is exactly 2 times D2, and so since they're scalar multiples of each other, that means they are parallel lines. So it's just a good thing to check before you go ahead. So again, we need to find QP, so we just need to take some point on one and some point on another, and then we need the direction vector. So I'm going to take point Q to be 3, 2, negative 2, and then P to be 1, 1, negative 3. So let's take Q. Now I'm just reading these off from here, right? 3, 2, negative 2. I can just read off that point, which is going to give me Q, and then I can just read off 1, 1, negative 3 to give me a point on the first line. And then I find QP, this vector, to be 1 minus 3, 1 minus 2, negative 3, subtract negative 2, and that ends up being negative 2, negative 1, negative 1. And actually what I'm going to do here is realize that since the order here doesn't matter, and if you think about the formula, it's the length of the cross product. If I change the sign, the direction of the vector, so I use 2, 1, 1 instead, that's not going to change the length. So I can just take PQ instead. So I'm going to use PQ instead, which is just 2, 1, 1. I mean, these lines don't have an order to them, right? It's not like it's a first line, second line. I could call the first line the second line, the second line the first. So I can just as well use PQ. So I'm going to go ahead and do that just to algebraically not have to worry about the minus signs. Okay, and then we got a direction vector. And the direction vector, again, we can read off. We already found it up here. It's 2, 1, 2. Remember, I can always use the one that's simpler because any non-zero scalar multiple of a normal or a direction vector is still a normal or direction vector. So our distance is the norm here of PQ crossed with D divided by norm of D. So this is coming from the formula that we got for the distance between a point and a line in 3 dimensions. I do need to figure out the cross product, so I'll do that just on the side up here. So that is my cross product. So I've got the norm of 1 minus 2, 0, all divided by the norm of 2, 1, 2. So on top, that's going to be square root 1 plus 4. On the bottom, square root 4 plus 1 plus 4. So that makes a square root of 5 over square root 9, so square root of 5 over 3. And that's approximately equal to 0.75. Now we come to a very important case. This is super important, maybe the most important case of all, and that's the distance between a point and a plane in 3 dimensions. So the reasoning behind this one is virtually identical to when we were finding the distance between a point and a line in 2 dimensions. Everything's just bumped up 1 dimension. So again, we're going to assume we have a point P that's not on the plane, a point Q that's on the plane. We're going to find this vector from Q to P, and then what we really want is the normal component of this. So we want the magnitude of the normal component of this. So we want that distance. Sorry, I changed my normal. Didn't quite look normal enough. So we want our distance now to be this absolute value of the component of QP along the normal, which again is equal to the absolute value of QP dotted with the normal divided by the length of the normal. Now, if you remember, we also got a special case. If we were given the equation of the line, we were able to get a nice formula for that. There's the same thing here. If this plane is given by a nice equation, say ax plus by plus cz plus d is equal to 0, then we can do pretty much what we did before. So what we're going to do is read off the normal from the coefficients, and then just plug in what we know about the components of QP, and everything's going to kind of fall out. So if the plane is given by equation ax plus by plus cz plus d is equal to 0, then the normal, again, we just read that off here, a, b, c. And then QP, of course, is equal to x1 minus x naught, y1 minus y naught, z1 minus z naught. And let me move this down a bit. And now we can go ahead and substitute in, so we get the distance is, okay, so it's going to be the absolute value of a x1 minus x naught. So this should look very similar to what we did before. If you go back and look at what we did with the distance between a point and a line in 2 dimensions, there's just an extra stuff with z. Now, if you remember what we wanted to do here, we really wanted to add and subtract the constant here. So I'm going to go ahead and do that, thinking back to where we were before. We need a plus d minus d, and this is all going to be divided by square root of a squared plus b squared plus c squared. That's the length of the normal. So on top, we've got, if I distribute through, again, ax1 minus ax naught, by1 minus by naught, cz1 minus cz naught, plus d minus d, and because Q is on the plane, we know that ax naught plus bx naught plus that should be by naught, plus d is equal to 0, which means that, all of those go away. So all we're really left with is, again, taking the left-hand side of the equation of the plane and just plugging in the point that's not on the plane, plugging in the coordinates of the point that's not on the plane. Same as the formula before, except there's an extra z term on top, and there's the c squared on inside the square root on the bottom. Okay, so let's look at an example. We're going to find the distance from the point 2, negative 3, 4 to the plane x plus 2y plus 2z equals 13. Again, probably the most important thing not to forget here that people forget. Subtract 13. So it's x plus 2y plus 2z minus 13 is equal to 0. Super important that you don't forget that. Okay, now we just plug in. So absolute value, I'm going to plug into the left-hand side over here. So I'm going to plug in 2, negative 3, 4. 2 plus 2, negative 3 plus 2 times 4 minus 13. And it's all this divided by the square root of 1 plus 4 plus 4. Okay, so on top here we've got 2, that's negative 6 plus 8, so what does that make? 10. Subtract 19. Okay, so we would get negative 9 inside there, but it's an absolute value, so positive 9. And then on the bottom, of course, square root 9. Okay, so it's 9 over 3, so we get a distance exactly equal to 3. Okay, very nice. We're just about there. We got a couple more cases to go, a few more. Let's find the distance between a line and a plane in 3 dimensions. So this is pretty much like the previous case. you just need to check two things. Well, you need to check one thing. You need to check that the line really is parallel. In other words, you need to check that direction vector for the line. So say this was a direction vector here, d. You need to make sure that when you dot it with the normal vector for the plane, that really gives you 0. And then you need to find just a particular point P on the line. And that's usually not difficult. Okay, so let's look at an example of this. So we're given the equation of the planes, 2x minus y minus 4z equals 5, but we're given the line in symmetric equations. So you have to remember how to go from symmetric equations to parametric form. If we set all of these equal to t, and then solve for x, y, and z. So if we set x minus 1 over 3 equal to t, we see that we get parametric equations for the line of x is equal to 1 plus 3t, y is equal to 2 minus 2t, and z is equal to 3 plus 2t. Notice that you can read off the direction vector here. You don't have to actually write all this out. You could just read off the direction vector from the denominators, as long as you make sure that the numerators have, it's just 1x, 1y, and 1z. So in that case, you can just read these off. So a direction vector here would be given by 3, negative 2, 2. And we just need to dot that with the normal, which remember comes from the coefficients here. 2, negative 1, negative 4. So let's go ahead and check that. D dotted with n is equal to 6 plus 2 minus 8. 3 times 2. Negative 2 times negative 1, 2 times negative 8. So that is 0, and we're happy. We really have a line that does not intersect the plane. Okay, so all we have to do now is find a point, and we can read off a point P on the line by taking the other numbers that we have in these parametric equations. So that's just the 1, 2, 3. By taking t, just set t equal to 0. So we've got our point, 1, 2, 3. We've got our equation of the plane up here, 2x minus y minus 4z equals 5. So we're all set up, if we remember that this is minus 5 is equal to 0. Don't forget that. We're all set up to say our distance. So our distance is going to be absolute value of 2 times 1, and we're just plugging in 1, 2, 3 up there, so 2 times 1 minus 2 minus 4 times 3 minus 5, all divided by the square root of 2 squared plus 1 squared plus 4 squared. Okay, so let's see, those terms go away. We've got a negative 12 minus 5. I guess that's negative 17 is going to make 17 divided by a square root of, what is it, 16, and 4 is 20, and then another one, square root 21. So 17 over square root 21, and that is approximately 3.71. All right, next we're looking at the distance between parallel planes. So again, in this case, there's basically two things we need to do. First, we need to check that the planes really are parallel, and that just amounts to checking the two normals. So if I look at normals n1 and n2 here, I just need to check that those are scalar multiples of each other. And then I need to find just a single point, a particular point on one of the planes. And then I can use the formula for the distance between a point and a plane, as we've done already twice. So let's find the distance between the planes x plus 2y minus 6z equals 1, 2x plus 4y minus 12z equals 5. Again, let's check the normals here. I read off the coefficients 1, 2, negative 6. And for this plane, n2 is 2, 4, negative 12. And I see that n2 is exactly equal to 2 times n1. So that's great. I know that these are now parallel planes. And really, I have a lot of freedom as far as what point and which plane to choose. Since x plus 2y minus 6z equals 1 is going to be a little bit easier to plug into, what I'm going to do is choose a point on the other one. So I'm going to choose my point, P, to be 5 halves, 0, 0. So I can just set y and z to be equal to 0. So 5 halves, 0, 0. That's on the plane 2x plus 4y minus 12z is equal to, is equal to 5. And then the other plane, let's just remember that we need to subtract the 1, so it's x plus 2y minus 6z subtract 1 is equal to 0. And now this is all set up for me to plug and chug, so I go in absolute value. So I'm going to plug in 5 halves, 0, 0 into the left-hand side of the other plane. So that's going to give me 5 halves plus 0, minus 1, all in absolute value, divided by square root of 1 squared plus 2 squared plus 6 squared. So it turns out to be 3 halves, divided by, that's 36 and 1, 36 and 4 is 40, another 1 square root 41. Okay, so I get my distance to be 3 over 2 square root 41. And that is approximately 0.23. So hopefully you can see here how important it is to remember that formula for the distance between a point and a plane. We use it not only to find the distance between a point and a plane, it's also the easiest way to find the distance between a line and a plane and two parallel planes. We have one last case to get to, and then we're finally done. We're going to look at the distance between skew lines in 3 dimensions. So let's say that these were 2 skew lines, and we're in R3 here. So what the idea is to take a point on each line. So we're going to take a point P here and say a point Q here. And the idea here is that these 2 skew lines can be placed inside of parallel planes. And we can find the common normal to these 2 planes by taking the cross product of the direction vectors. So if we have direction vectors d1 and d2, then if we take the cross product of these, this has to be a normal to both of these planes. Okay, why is that? Well, the normal to these 2 planes has to be orthogonal to d1, because d1 lies inside the one plane, and it has to be normal. It has to be orthogonal to d2 because d2 lies in the other plane. So that's the first step. Is first take the cross product of the 2 direction vectors, and that gives us the normal d1 cross d2. And now what we're going to do is find this vector PQ. So we're in the case of finding the distance between a point and a plane. So we're going to find the distance between the point P and the plane that contains the line that contains Q. So we're going to form the vector PQ. This could be any point on one line to any point on the other one. But if these lines are given in parametric form, then usually you just, you read them off from the parametric form. And then we're going to use, finally, distance between a point and a plane, which is given by the distance is the absolute value of the component of PQ onto n, which we remember is the absolute value of PQ dotted with n, all divided by norm of n. Okay, this is, I think, the quickest way to do this. Again, there's different ways to find the distance between skew lines, but I think this is the easiest to understand, the easiest to carry out. Oh, and we should check that these are skew. So let's go over checking that these are skew. Okay, so D1, if this is L1 and this is L2, D1 is going to be 7, 1, negative 3. D2 is negative 1, 0, and 2. So those are clearly not scalar multiples of each other. The only thing left then is to make sure that there's no, that these don't intersect at all. So if we set 1 plus 7t equal to 4 minus s, that would mean that s is going to be equal to 3 minus 7t. And now if we substitute that into each of these equations here, well, the second one we'd get 3 plus t is equal to 6, which would imply, of course, that t is equal to 3. Okay, so that means now we can substitute back in, see that s would be 3 minus 7 times 3, be 3 minus 21. So we'd have to have s as negative 18 and t is 3, but that's going to be inconsistent with z, because 5 minus 3t then would be 5 minus 9, negative 4, but 7 plus 2s is 7 plus 2 times negative 18. That's clearly not negative 4. Okay. So these are skew lines. So we start off calculating the normal, and then we can apply the formula. Oh, we need to find PQ first. Okay, so P, so we can take P to be 1, 3, 5. Just take T equal to 0 and S equals 0. So we get 1, 3, 5. We could take Q to be the 4, 6, 7. And that would give us PQ, let's see, it'd be 3, 3, 2. 3, 3, 2. Okay, now we have PQ and we have our normal, so now we can plug into the formula. So PQ dotted with the normal, let's say it's going to be 3 times 2 is 6, minus 33, plus 2 times 1 plus 2. All divided by the length of the normal. So the normal is 2 minus 11, 1. Okay, so that's going to be 4 plus 121 plus 1, which is square root 126. And on top, we've got 25. So it's negative 25, but it's the absolute value. So altogether, we get 25 divided by square root 126. You can reduce this a little. Even if you don't rationalize it, you can clean it up a bit and get that this is 25 divided by 3 square root 14. And that turns out to be about 2.23. Okay, so that would be the distance between the skew lines. And with that case, we've pretty much done all the different cases. So we've gone over all the different possibilities of different distances that you might need to calculate in 2 and 3 dimensions between points, lines, and planes. So I hope this video was helpful. I really tried to find the easiest ways to understand how to calculate these distances and what's going to be computationally the easiest to carry out.